Hey class, Adam Ward here, our third and final lecture video for Open Channel Flow Part 2. We've talked about gradually varied flow, we've talked about uniform flow, and in our last video we did an analysis of hydraulic jumps. What I want to do in this final video for today's lecture is work through a hydraulic jump example problem. So here's a setup for us. Hydraulic jumps do happen in nature. They also happen when we're, for example, accelerating flow over a dam. And as you can see in the top right condition, what you'll often see downstream of a dam is that we end up with supercritical flow coming down the face of our structure. And we want to cause a hydraulic jump to happen to help dissipate energy where we want it before that subcritical flow exits into the natural stream. Now, if you chose not to do this and you just let that hydraulic jump occur where it wants, two things will happen. One is it may move up and downstream in response to depth of flow, for example, or volumetric flow rate. But more importantly, all of that energy is going to get, much of that energy is going to get exerted in moving sediment. So you're going to take what we often call stream power and you're going to apply that to the bed. And you'll scour out and erode out the toe of that dam. And that puts the dam at risk and is not good for the environment. So what we do then is downstream of the dam, we add blocks to basically force the hydraulic jump to happen where we want it. So in the top left panel, you can see an image of these in a real world setting. In the bottom of the slide, you can see a schematic of how this might work. The idea here is, again, we want to control the hydraulic jump. So we want to be able to dissipate the energy essentially where we've put concrete that won't be eroded by that and protect the downstream ecosystem as well as protecting the integrity of the dam. So our objective today is going to be, given information about what's coming over a dam, what would be the velocity and depth that would exit one of these sets of baffle blocks that would cause the hydraulic jump. So to make this problem a little more tangible for us, let's envision we've got a dam, we've got those blocks down at the bottom causing a hydraulic jump. So for a dam that is 100 feet wide, meaning in and out of the screen, and a depth of flow coming over the dam of 0.6 feet and a velocity of 18 feet per second when it reaches the hydraulic jump, what will be the downstream depth and velocity? Okay. So this is meant to be an exercise, so at a few points I will pause and ask you to reflect on what you think the next steps are. So you can see I've already written we want to confirm the upstream is supercritical. This would be the appropriate time for you to do that, but also to lay out what you think is your strategy for the problem. How are you actually going to use the knowledge that you have to find what's unknown? So go ahead and hit pause, think through this, give it a try, and then unpause and I'll come back with my solution. All right, folks, welcome back. Step one, let's define some points in this problem. I'll pick point 1 as upstream of the hydraulic jump and point 2 as downstream. And before we go too far, we want to really confirm that this is going to be a hydraulic jump, that we do have supercritical conditions on the upstream side. Of course, we do that with the Froude number. So 18 feet per second in the numerator, the velocity, and in the denominator, the square root of 0.6 feet, the depth, y1, multiplied by gravitational constant. I get a Froude number of 4.10, so I am confirming this is supercritical flow coming off the dam, and we could proceed with the equations that we've been deriving in today's lecture. So at this point, you all should have a sense of how to proceed. If you haven't thought about it, again, I'll encourage you to pause the video here and actually think, what will I do now that I know a hydraulic jump is possible? Okay, so you've got your plan, I'll show you mine. I'm going to start by finding the depth on the downstream side of the dam. And so to do so, I'm going to grab the equation that we derived using conservation of momentum and conservation of mass. Y2 over Y1 equal to 1/2 times the quantity minus 1 plus the root of 1 plus 8 times the upstream Froude number squared. Whew! All right. So plugging in some of those values, we have conveniently already calculated the Froude number at point number 1. It's 4.10. And when I work through this calculation, I get a ratio of 5.32. That's not quite the answer yet. I know that the ratio is equal to 5.32, so I could use that plus my knowledge of y1 to solve for y2. And when I do so, I get a downstream depth of 3.19 feet. So that's y2. We don't yet have a calculation for v2. That's the other thing that we were given. So what are you going to do now to find v2? Again, let's pause here, give it a shot on your own, and then unpause to see how I solve it. All right, good job giving that a shot, everybody. For velocity 2, I'm going to just use conservation of mass. I know that volumetric flow in must equal volumetric flow out. And as we've been doing, I can sort of substitute those into A1 V1, or even change area into width B multiplied by depth Y times velocity. Those widths, of course, cancel out. And it's straightforward then to know that Y1 V1 is going to equal Y2 V2. And I can solve for a downstream velocity, a V2, of 3.39 feet per second. Now, at this point, it would be prudent to check your work. One way that you can check it is to make sure that a hydraulic jump actually occurred. What is that Froude number for the downstream section? Plugging in the values that we've calculated, I get a downstream Froude number of about 0.33. So it is subcritical flow downstream of the hydraulic jump. That's what we expected. That's a good check just to make sure that my calculations have gone correctly. If I got a Froude number of greater than 1 at that point, I would want to loop back to the calculations that I did both in red and blue pen, looking for somewhere I might have made a typo. Now, strictly speaking, this is what you were asked for in the video. You have found Y2 and V2. I want to show you just a couple extensions to link this back to some other work we've done in this class. So one of those extensions is how much power is dissipated by the jump. And of course, power is energy per time. So if we know the head loss across the jump, we could calculate the power that's dissipated. And so for this problem, that calculation looks something like this. You'll notice right here, I have solved for a head loss of 2.26 feet. I will show you on a subsequent slide exactly how I did this, or a graphical way that I did this, but you could also try to calculate that yourself using the head loss equation that we derived in our previous video. So for this calculation, I end up with about 1.5 times 10 to the 5th foot-pounds per second, or about 277 horsepower as the amount of power that's being dissipated by those blocks. Now, the last thing that I want to show you all is what this means in terms of specific energy. Right? And so for our specific energy diagram, of course, we have depth of flow on the y-axis and our energy on the x-axis. And you all are used to seeing me draw it with this diagonal one-to-one line on there. For a given flow rate, we have something like this. Now, you'll remember, of course, that we could calculate energy at point 1 as y1 plus, let's see, v1 squared over v1 squared over 2g, I think. And we know that we were in the supercritical state. And so if we do those calculations, we would end up with E1 and Y1 somewhere like this on our specific energy diagram. Right? And if I'm remembering correctly, E1 is about 5.3 feet. You can do that same calculation for E2, and it ends up being about 2 feet. And so E2 is approximately here on our diagram. And we have gone through the calculation to identify Y2. And again, that Y2, this was about 3.3 feet of depth. And you'll remember from the given, Y1 was about 0.60 feet. Right? And so plotting it out on the specific energy diagram, I think, is a helpful exercise for us because it helps give you a sense of what's actually happened in the problem. Right? What the hydraulic jump did was it started at point 1, it ended at point 2, and we transitioned through that standing wave at the critical point around the specific energy diagram up to the subcritical arm. Now you'll notice that I've left E2 at a much smaller value than E1. Right? What happened there, this distance, E1 minus E2, is the head loss. And so, as I calculated on the previous slide, this was about, I think it was about 2.26 feet. So you can use the specific energy diagram to your advantage. Right? What I've just shown you guys in red is the energy equation as we applied it to our hydraulic jump. So this sort of drawn in yellow pen here from 1 to 2 is what happens on the specific energy diagram for a hydraulic jump. Not only are we going from the subcritical arm to the supercritical arm, but we've had a net loss of energy due to that turbulent mixing. So E2 is to the left of E1 because you have less specific energy downstream of the jump. How much less? Well, that's equal to the amount of head loss that was that occurred, or the amount of energy dissipated in turbulent mixing. All right, folks, I hope that this exercise showed you how to take advantage of these hydraulic jump equations, and in particular how to map some of this back onto the specific energy diagram that we've looked at in the past. That's what I've got for you today, and I will see you in lecture. Thank you.